the risky fault lines right here in the United States. There are many.
The state's emergency management agency is encouraging Mississippians to participate in the Great Shakeout earthquake drill.
That area lies along the New Madrid Fault.
Until a weak earthquake in northwest Mississippi, the United States Geological Survey has...
That's bad news for the Mississippi.
Amtrak service along the Gulf Coast.
What if we told you that beneath the calm, silty waters off Mississippi's coast, something is shifting? Not just small tremors or sediment movement. We're talking about hidden fault lines, heat anomalies, and deep earth gases bubbling up from below. Until now, the northern Gulf of Mexico was considered quiet, geologically stable. But that assumption, it's being shattered. Because what scientists just detected beneath Mississippi's coast.
Today, we're visiting the Mississippi Gulf Coast, which is great for hanging out at the beach, boating, fishing, and gambling.
Might be the early warning sign of something much bigger. Ancient faults reawaken beneath the Gulf. Using a mix of satellite altimetry, underwater sonar, and newly installed ocean bottom seismometers, researchers from NOAA and several universities have discovered something unexpected, something that is reshaping our understanding of the Gulf's geologic past and future.
Yeah, the weather conditions are getting worse and worse as the storm draws closer to the coast. Take a look at those palm fronds and the trees blowing very, very strong. The weather is getting a whole lot worse. Heavy rain.
Just south of Biloxi and Pascagoula, buried beneath a thick, shifting layer of sediment and salt, lies a network of ancient fault lines. These faults, etched into the Earth's crust during the early formation of the Gulf of Mexico.
The Gulf of Mexico is the Wild West of the sea, and it's every man for himself.
Were long believed to be dormant remnants of ancient tectonic shifts. However, new data show these geological scars may be far from inactive. The instruments have recorded subtle yet persistent changes, crustal uplift measured in centimeters over just a few months, shallow seismic swarms occurring in irregular bursts, and early indications of slow slip events, those silent, creeping movements that release stress without traditional earthquake shaking. These movements often go unnoticed without highly sensitive monitoring equipment, yet they represent a transfer of tectonic energy that can accumulate and later trigger larger seismic events. To deepen their analysis, scientists launched autonomous underwater vehicles, AUVs, equipped with fine-resolution sonar and gravimetric sensors.
Using the latest underwater scanning technology, piercing the deep oceans and turning the accurate data into 3D images.
These AUVs mapped long linear ridges and troughs on the seafloor, features consistent with active faulting. Some displacements extended for dozens of kilometers, crossing through sedimentary zones once thought to be stable. This structural deformation is not random. It aligns closely with stress directions observed in other intraplate fault zones worldwide. Sediment cores drilled near the active regions revealed evidence of recent disturbance. Disrupted layering patterns, microfractures in compacted shale, and traces of mineral-rich fluids were all present, clear signs of geomechanical activity. In some cases, entire layers had been vertically offset, suggesting vertical fault motion in addition to the more common lateral slip. Perhaps most concerning are the patterns of microseismicity detected by the seafloor instruments. Rather than isolated events, the data suggests that seismic energy is migrating laterally along connected fault branches. This cascading behavior has been observed in other tectonic systems before major earthquakes, where small tremors act like dominoes, sequentially weakening fault zones until a threshold is reached. To the untrained eye, the Gulf floor appears tranquil, its murky depths betraying no hint of turmoil. But the instruments tell another story, one of mounting tectonic tension, of ancient fractures stirring back to life beneath one of America's most vulnerable coastlines. Pressure beneath the oil fields, The Gulf of Mexico's oil economy isn't just an engineering marvel. It may be an unintended geophysical experiment. For decades, industrial activity has reached deep into the Earth's crust, tapping into reservoirs once thought untouchable. Each drilled well, each extraction point, subtly alters the stress landscape beneath the seafloor, sometimes in unpredictable ways. Studies have shown that when fluids are removed from deep reservoirs, the surrounding rock can compact, shift, or even collapse. This isn't always a gradual process. In some instances, sudden pressure drops can destabilize fault zones that were previously in delicate balance. Such destabilization can lead to small, frequent tremors or potentially larger, more destructive quakes if the accumulated strain reaches a critical threshold. Adding to this complexity is the widespread use of reinjection wells. These wells are often employed to dispose of wastewater or to enhance oil recovery by injecting fluids back into the ground to maintain reservoir pressure. But these reinjected fluids don't remain in isolation. They can migrate laterally along permeable strata, sometimes intersecting with tectonic faults. When this happens, the increased pore pressure can reduce the effective friction along fault planes, making it easier for them to slip. In Mississippi's offshore fields, some reinjection operations spatially overlap with clusters of newly detected microseismic events. While correlation doesn't inherently prove causation, the temporal and geographic overlap is raising concern. Researchers are now deploying more sensitive seismic instruments to monitor whether these injection sites are subtly influencing regional tectonic stress. Some models suggest that even small perturbations in pressure on the order of tens of kilopascals can be enough to trigger movement along critically stressed faults. Furthermore, seismic reflection surveys and borehole data suggest that the subsurface geology in these areas is riddled with complex fault networks and fractures, many of which were undocumented until recently. This fractured architecture means that injected fluids have more pathways to migrate, increasing the uncertainty and scale of potential impact. Adding to the risk is the cumulative nature of these operations. While one injection site may have a limited effect, the combination of dozens or hundreds of such sites operating in tandem may act like a distributed force, quietly altering stress fields over large areas. Some geologists have likened this process to the tightening of a violin string. Each twist adds tension until the system suddenly snaps. Could our energy infrastructure be nudging a once dormant fault system back to life? It's a question that no longer seems speculative, but increasingly urgent. The seafloor is breathing. Recent high-resolution sonar scans have revealed a striking phenomenon: periodic bulging and subsidence across the seafloor. These slow, rhythmic vertical movements have led researchers to describe parts of the continental shelf as breathing. This isn't just a poetic metaphor. It's a measurable geophysical process. The cause? Likely a combination of fluid migration from deep crustal sources and elastic rebound from fault slip. These movements, although subtle, signal active deformation in the Earth's crust. More importantly, they may indicate zones where energy is accumulating, a potential precursor to seismic events. In some cases, scientists have detected a repeating cycle of seafloor uplift over months, followed by sudden relaxation, suggesting that pressure is being stored and periodically released, perhaps through minor fault movements or fluid expulsion. Further investigation using pressure gauges and gravimetric sensors has revealed minute but consistent mass redistribution beneath these zones. This indicates not only physical movement, but also internal material shifts, which could reflect subterranean fluid migration or the slow reactivation of deep-seated faults. Importantly, these breathing patterns are not evenly distributed. They seem to concentrate along structural weak points, particularly where sediment layers are thickest and intersect with known fault lines. What's particularly concerning is that these zones of uplift and subsidence are appearing near key infrastructure corridors. Pipelines, data cables, and even anchor points for offshore rigs are all potentially vulnerable to long-term strain. A slight tilt or shift, repeated over years, can weaken welds, displace anchors, or bend joints, leading to systemic degradation that standard inspections may miss. Without adaptation, the risk of slow burn failure rises, failures that may go unnoticed until disaster strikes. Engineering teams are now being advised to incorporate geodynamic monitoring into their maintenance schedules, as the once static seabed may no longer be reliable ground. Unseen risks to drinking water and aquifers. Most discussions around seismic risk focus on buildings, roads, or industrial sites, but another vulnerability lies underground within Mississippi's aquifer. Earthquakes and subsurface fluid migration can drastically alter groundwater dynamics. If fault zones shift or fracture aquitards, impermeable layers that trap clean water, saline or contaminated water could seep into freshwater reservoirs. In other regions, such as Oklahoma and Central California, increases in seismic activity have been linked to rising arsenic levels in public water supplies. These incidents often follow the reactivation of faults that slice through aquifer systems, enabling chemical elements trapped deep underground to migrate upward into potable water sources. Mississippi's coastal aquifers are already under pressure from over-extraction, agricultural runoff, and the encroachment of salt water due to sea level rise. A tectonic disturbance could dramatically worsen the situation. If seismic activity alters the natural gradients that keep salt water at bay, brackish water could intrude inland faster than current models predict. Additionally, shaking could damage well casings and disrupt groundwater flow paths, leading to long-term degradation of water quality. The infrastructure to monitor and respond to such changes is limited. While surface water treatment facilities are designed to filter out known contaminants, deep aquifer contamination, especially from heavy metals and naturally occurring radioactive materials, requires specialized equipment and long-term mitigation strategies. Contaminated drinking water would not only pose a public health crisis, it could force entire communities to abandon local water sources, triggering economic displacement and amplifying regional inequities. Heat rising from below. In one particularly alarming discovery, researchers detected rising heat just offshore. Thermal sensors placed on the seafloor recorded temperatures up to 10 degrees Celsius higher than normal, suggesting unexpected geothermal activity. Such temperature deviations were not isolated. They were found concentrated in linear zones, consistent with mapped fault lines. These hotspots formed a thermal fingerprint that aligned with regions of seismic stress accumulation and recent microfracture activity. Where is that heat coming from? The most likely explanation is friction. When crustal blocks rub against each other under immense pressure, heat is generated at the fault interface. This geothermal energy can accumulate in zones where movement is intermittent or partially locked, producing significant thermal gradients over time. In high-resolution thermal imaging, these zones appeared as warm streaks etched into the seafloor, indicating frictional heat release along fault plane. However, friction isn't the only possible source. Scientists also propose that these heat anomalies may result from hydrothermal circulation, where seawater percolates down through fault cracks, heats up in the deep crust, and rises back toward the seafloor. This process can form underwater hydrothermal vents, similar to those found at mid-ocean ridges, although generally at lower temperatures. Even more intriguing was what the rising fluids contained. Samples pulled from the seabed showed bubbles of methane and helium-3, a rare isotope that is almost never found near the Earth's surface unless it originates from the mantle. Helium-3 is particularly valuable as a geological tracer because it's not produced in large quantities in the crust. Its presence here suggests deep Earth pathways are opening or reactivating, allowing gases to rise along newly mobilized fault structures. Additional chemical analyses of the fluid samples revealed elevated levels of other mantle-derived elements such as radon, carbon dioxide, and isotopically light helium-4, which further supports the hypothesis of deep-sourced activity. These geochemical signatures resemble what scientists have seen in tectonic rift zones and volcanic arcs, where magma and superheated fluids rise through fractured rock. Sub-bottom profiling and magnetotelluric surveys added another layer of evidence. Beneath the hotspots, researchers identified zones of anomalously low electrical resistivity, a common marker for the presence of fluids or molten rock. Combined with the gas samples and thermal data, the findings paint a picture of a dynamic, pressurized system developing beneath the Mississippi coast. This isn't just tectonic activity. It may be the earliest stage of a broader geodynamic shift. The region may be evolving from a passive sedimentary margin into a more active tectonic boundary. If confirmed, this would mark a fundamental change in the way scientists understand the Gulf's long-term seismic potential. It might be a conduit, an opening from the deep earth, signaling that far more is happening beneath the Gulf than previously imagined. Why now? The perfect storm of forces. But why now? Scientists believe a complex interplay of natural and human-induced factors could be influencing the situation, each exacerbating the others in unexpected ways. Third, broader environmental changes are playing a critical role. Rising sea levels, driven by global climate change, are increasing the weight burden on the ocean floor. This additional pressure can affect fault stability, especially in regions already strained by other factors. Similarly, shifting sediment loads from the Mississippi River Delta are altering the mechanical properties of the seafloor. Massive amounts of sediment deposition, followed by compaction and slumping, can trigger differential loading across faulted zones, further enhancing instability. Compounding all these issues is the natural subsidence of the Gulf Coast itself. As ancient sediments compact under their own weight and fluid withdrawal accelerates this compaction, the entire region is sinking. This gradual subsidence, combined with sea level rise, exacerbates coastal vulnerability, both by physically lowering the land and by subtly shifting the stress fields deep underground. The culmination of halokinesis, anthropogenic drilling impacts, environmental loading changes, and natural subsidence creates a perfect storm of geological instability brewing beneath Mississippi's coast. Scientists warn that such compounded effects are nonlinear, meaning their combined impact is greater than the sum of their parts, and could dramatically accelerate tectonic awakening in this historically quiet zone. A fragile coastline at risk. The implications are serious and far more complex than previously imagined. Mississippi's coast is home to a dense web of critical infrastructure, offshore oil and gas platforms, thousands of miles of underwater pipelines, high-capacity internet and communication cables, and ports like Gulfport that are essential to regional and national commerce. Much of this infrastructure was engineered with hurricanes in mind, not seismic activity. The structural design codes focus on wind shear, storm surge, and corrosion, not the lateral displacement or vertical rupture that even a moderate earthquake could cause. The risk doesn't end at sea. Onshore, the threat becomes personal. Cities like Gulfport, Pascagoula, and even parts of Mobile lie on what geologists call unconsolidated water-saturated sediments. In the event of strong shaking, these soils can undergo liquefaction, a process where stable ground turns into a viscous slurry. Buildings tilt, roads crack, and foundations can fail catastrophically, even if the quake's epicenter is miles away. Emergency responders would face chaos, blocked evacuation routes, disrupted water and gas line, and overwhelmed hospitals. Local economies also face a major vulnerability. The Mississippi River's shipping channels and offshore oil platforms feed into the national energy supply chain. Damage to any one of these nodes could disrupt deliveries, drive up prices, and require months, if not years, of recovery and repair. All of this reinforces one urgent truth. This stretch of the Gulf Coast was never prepared for tectonic threats. And if the science is right, it may need to be Soon. So, is Mississippi's coast on the verge of a tectonic reawakening? It's too soon to say for sure, but the data are clear. Something is happening beneath the Gulf, something we can no longer afford to ignore. As scientists continue to study these anomalies, one thing is certain: this forgotten corner of America may be hiding one of its most unpredictable geological threats. Subscribe for more discoveries unfolding beneath our feet, because the Earth is never truly still.